In this lesson, we're going to learn a more algebraic way of solving a system of equations. So in the last lesson, we saw how we could graph two lines and see the point of intersection where they cross. But notice that that requires us to be very neat. And what if the point of intersection happens to be a fraction? How could we find out exactly what that value is? So instead, we're going to solve a system of equations using a more algebraic technique. This is referred to as the substitution method. In the substitution method, we're simply going to pick one of the two equations and try to get any one of the variables by itself. So in this problem, we're going to go ahead and pick the x from the first equation. There's no particular reason we did that. It just happened to be the first variable that we saw. So if we get x by itself, we simply have to subtract y, and we find out that x is equivalent to 6 minus y. So the x coordinate for my answer is 6 minus the y coordinate. Well, if we circle both sides of this new equation, that really indicates in our own mind that x is in fact the same as 6 minus y. So we can now take that answer and substitute that whole expression of 6 minus y into x in the other equation. So this other equation was x minus y equals 2. And since x is the same as 6 minus y, I can now write it as 6 minus y equals 2. And the advantage of this is that now we only see one variable, which we can now solve. So this gives us 6 minus 2y equals 2. And now if I subtract 6 from both sides, that gives me negative 2y equals negative 4, which gives me my first part of my answer. So I know that in order to make this system of equations true, the y coordinate needs to be 2. Now the advantage of the substitution method is that in the first step, we got x by itself and put that in terms of y. So we can now take that value of y, which is 2, and substitute it back into this equation here in order to solve for x. Now we could plug that y equals 2 back into any one of the original equations as well, but we chose to plug it in here so x is already alone. And therefore 6 minus 2 is equal to 4. So if we were to graph both of these lines, we would find out that that point of intersection is 4, 2. But we didn't have to graph in order to solve this system of equations. Let's try one that's a little more complicated. Here we've now got coefficients in front of each of the variables. Well, notice that the easiest variable to solve for would be y in this first equation. So that's exactly what we're going to try to do. We're going to try to isolate variables that have coefficients of 1. Now, if we don't have a variable with a coefficient of 1, then that's when it's going to be beneficial to use another method that we'll learn in the next lesson. So in this case here, we're just simply going to subtract 3x, and we get that y is equal to negative 3x plus 10. We just shifted 3x to the right side. We can now take that negative 3x plus 10 and replace that with y in the second equation. And so that gives us 2x minus 5 times negative 3x plus 10 equals 1. So again, we just replaced the y coordinate with the expression negative 3x plus 10. Now if we distribute, we get 2x plus 15x minus 50 equals 1. And the advantage of this substitution method is that now we have a single variable to solve. Here we get 17x, and if we add 50, we get 51. Divide by 17, and we find out the first part of our point of intersection, which is x equals 3. But again, that's only half of our answer. We want to now find the y coordinate, which is why we could plug x into this variable, or we could plug x equals 3 into this variable. But it's actually best to plug it into this equation here, since y is already alone. So we say y equals negative 3 times 3, which is negative 9, plus 10, which means that the y coordinate is 1. Now I encourage you to always plug these values in to each equation to make sure that it works. So therefore, our point of intersection, if we were to graph, would have been 3, 1. And let's see why that works. If I replace x with 3 and y with 1, 3 times 3 is 9, plus 1 is 10. If I replace x with 3, I get 6. If I replace y with 1, I get 5. 6 minus 5 is 1. So notice that this is in fact the correct point of intersection, and we can always check to see if we're correct by just plugging it back into both equations.